Hey guys, and welcome back. So this is the geometry that we've been using so far, and with that I have also a wood structure, and this is the main platform. As you can see, this is carefully modeled so there's no intersection between anything, and everything is oriented in a specific way, so there's no, well, we can have random orientation, but it's like mimicking what a wood structure would look like. I'm not an engineer by any way, but this is something I put together to get some interesting shapes inside the building. And again, there is no intersection. Each one of these guys is a separate piece of geo. Each fragment, and this is very important to get the proper wood fracturing patterns. If we have shapes, if we have these guys combined, it's going to be very hard to create the wood grain and splinters that travels along this curved shape. Or if we had all this block together, it will be very difficult to get that. So I made sure that everything is separate so we can process it. Now this I then copy this 6 times to fill in all the interior pieces and have something that holds up this entire building. There is a huge gap in between this, and I wasn't too worried because I know I don't need this to be very realistic, but we're going to set up a constraint that will help make it solidify everything and actually enforce the concrete with the wood as it would do in real life. So let's take a look what we need for the wood. I'm gonna blast one of these guys. Not that. Okay, so we have this piece, and I wanna create the wood like fracture, and I'm going to generate some points. Okay, and let's fracture this. I'm gonna set this to 200. And right now we're just doing a basic Verna. As you can see, this is not looking like a wood pattern by any mean. And what I'm going to do is, what we want to do is to get elongated splinters that matches the curvature or the shape of the geometry. And in this case, we want them to be elongated along the y-axis. So what I'm going to do, this is a very basic trick to get the wood splinters, is to scale it down, scale the geometry size down, and then do the fracturing and then scale it back up. So I'm going to copy that and apply the inverse transformation. This is going to give me the elongated shards, and the more we scale it down, the longer the pieces are going to be. Okay, so that's how we get this pattern. Now the problem is with this, we're very lucky to get something oriented on the y-axis, but if we were to pick something else like these guys, this system will not work, because yeah, it's gonna flatten it like that, and then we're gonna get something that doesn't look like wood. So what we need to do is we need to orient this piece so that it's facing one axis. So let's first move it to the origin, and we need to do this, and then we can do the remaining process and apply the inverse transformation on that to put it back where it was. And you can see now it's looking like the patterns are correct. So for this, we need to do some matrices stuff and do some clever things to automatically reorient and align every piece to be aligned along the y-axis. Okay, and I have a small example here and we're gonna forget about this for now. I'm gonna talk about a different problem, a similar problem, but with a smaller example. So I have this plane here, okay, and I have a transformed version of this plane. I just put down a transform node, and I moved it. So let me copy this. So that's at the origin, and then I'm going to move it up and rotate it like that. Okay, so now if we just receive this geometry, we it's like that. It has this transformation applied to it, and if we wanted to transform it back, we need to figure out a few things to be able to do that. The easiest one that we can do is to transform this back to the origin, and the way we can do that is by taking, let's say this is the center of the object, point number 15. We compute a vector, which is the distance, the position of this point, and then we apply that vector back onto all these points. Okay, let's do this. I'm gonna vector pause 15, point 15. I'm gonna import the position of point number 15, and I'm gonna use the expression point. So 1, and I need the p position, the attribute p, and then the point number is 15. So now I have that information, and I'm going to take the position and negate that from p. Negate all these guys, negate this distance or this vector from all these points. I can do this easier. V at p minus 0.15. Okay, and if we take a look, we should see it snap back. Let's see, sorry, not 1, 0. The input is number 0. Cool. So you can see now we snapped everything back, and the next thing we need to do is we need to figure out the transformation. So we need to figure out a way to do this, basically. And for that, we need to create something called quaternion. And what a quaternion does, it's is a very simple, a very efficient way of storing transformation. Storing orientation. Okay, we have in a matrix we have either a 3x3 matrix or a 4x4 matrix. These are the two types that we generally use. A 3x3 matrix can contain a rotation or transformation only. The 3x3 can only hold this much information. A 4x4 can hold transform, scale, and rotation all at once. And it's a 16x16 float. It's a 4x4 float, 16 total. And the quaternion is a vector that holds just the rotation information. Okay, and to build a quaternion properly, we need two axes. We need an up vector, and we need something else that is orthogonal to that vector. So let's go back to here, and I'm gonna set this. I have this XYZ graph here. So this is my geometry, and we have X, Z, and Y. Let's say this. For example, this is my X, this is my Z's, and this is my Y. When I look at the geometry at 0, 0, I know that this relationship is always valid. So I have the Z-axis pointing this way, the X-axis, and the Y-axis. This is my alignment. Once we transform this guy, we took that orthogonal coordinate system, the Cartesian coordinate system, and we transformed that. And now we have the Z is pointing in a different direction, the X is pointing in a different direction, and the Y is pointing in a different direction. But the relationship between all of them is correct, is the same. They're always 90 degrees between each other. And to create a quaternion, to figure out the orientation of anything, we need two vectors that are orthogonal. So for this, we need to figure out a y-axis and a z or an x-axis, one of them. So if we take a look at the geometry and say, this is what we have. Let me turn this guy off. We have this geometry like that. What we need to do is we need to figure out a z-axis, an x-axis, and then from that we have an orthogonal plane. We have two vectors that describes a plane, a flat plane. We can compute the cross product of those two, and that will give us the y-axis, which will be orthogonal. And then we can take any two vectors, the z and up or the x and up, and compute a quaternion, generate a quaternion from that, which will tell us how much orientation or rotation has been applied to that geometry. And think of it as like this. Forget about the geometry, okay? Say we only have this guy, and then we transform this. We want to know how much rotation happened to that. And the quaternion doesn't care about the position, okay? We only going to look at it from a rotation point of view. Say we transform this back to the origin. Let's do this, so this guy. I'm going to transform this. Okay, so that's the, I'm going to move it up so it's, the 0 is at that point. The quaternion is going to allow us to see how much rotation has been applied to rotate this system from here to here. Okay, and that's the pivot point, 0, 0, 0. We're not going to worry about the transformation. That's really easy to fix. And we're going to create a few things in Vex and using point vaults to apply the inverse transformation that happened to this. We have two things. We need to transform this back to the origin, so that's the translate matrix, and we need to generate a quaternion based on two axes. And the way we're going to do that is, let me turn this off. So we have our grid, that's at the origin, and we have our transformed grid. What we need to do is we need to figure out the z-axis, the x-axis, and an up axis or a y-axis. And to do that, we're going to simply take point 15 and then take the closest, the neighboring points to 15. So the first neighbor is going to be this guy, number 11. We're going to compute a vector that travels like this, and that's going to be our z-axis. And then we're going to take the second neighbor, which is this guy, and we're going to compute another vector, and that's going to be our x-axis. Then we take those two and compute the cross product, which will give us the up axis, and then we're going to feed that into a quaternion, which will generate a 3x3 matrix that we can apply we can invert and apply to the geometry to rotate it back. Once we have this system working, we're going to apply it to these guys. Each one of them, we're going to apply the same thing. We're going to run into a problem, and we're going to fix that once we get there. So we'll continue in the next video. Thank you guys for watching, and see you in a bit.